Hello, everybody. This is Professor Ma, and this is summaries on the calculus, basic calculus in the polar coordinates. Okay, and so we're going to talk about how to find the slope of a tangent line to a polar curves, and we talk about how to find area enclosed, okay, area, and now we're going to the arc length formulas in polar form. Okay, let's start. We have this in xy coordinates. If I have a function y to f of x, there is something that we call this particular parameterizations. That is, we define x and y in terms of a third variable t, and then this each individually x components and y component in terms of as a formula in t as a system. Okay, and then this is called a standard parameterization by treating x the same as time. Okay, in polar coordinates, the variables are r and thetas. Okay, and we have theta is the angle, r is the distance out to the point, and we want to find again what is respectively the x coordinate and the y coordinate of these points, and we're going to express in terms of theta only. Okay, and in this case, x is r cosine theta, y is r sine theta. So we replace the r by the formula f. Now I get this we call the standard parameterization of polar coordinates for a polar functions. Okay, that is a formula between r and theta. Okay, and the reason we do this is because we're going to take derivatives. Okay, so let's say we have the formula r equal to theta. This is the this is a spiral. If this keep going on, and then you have the same bandwidth of spiral. Okay, so I want to put this into a parameterization polar coordinates, and that x is going to be in terms of theta. This that, y is that, and this is the standard parameterizations of the polyoids. Okay. Now we put things. We put x. We change the formula to investigate the tangent line of the polar curve. We put them first into the parametric form. Why? Because from last sections we know how to take the derivative of parametric forms. Okay, and dy dx. Okay, and so here's a problem. Basically, I have a tangent line right now. Okay, and I want to find the slope of tangent line. Slope of tangent line, of course, is delta y over delta x, right? The ratio of these two things. And this delta y delta x, how does it depend on r and theta? Because every formula having r and theta, but what I want to calculate is in the Cartesian coordinate of the delta y, pi, the rise over run. Okay, and then of course, then the parametric equation says, oh, that's easy. You just treat this as differentials, and then basically just a ratio with respect to the variable t in the parametric form. In our case, theta. Okay. But I know what y and x is. Now we're going to do the algebra. That is because I know the expressions of what y is or x is all the way in terms of theta algebraically. Okay. And so I take the derivative of dy dx. So I want that dy dx, which is the ratios of the two, the rise over run of the tangent line, or in terms of the angle theta and the distance formula r. Okay, is given by this formula. Okay. So this is the slope of the tangent line at the point r theta in the polar form. Our theta over here is in polar coordinates. Okay, and plotting x, y, and these, and then the slope of tangents. Now it's in x, y coordinate. Yeah, we can do it that way. Okay. Yeah, you make the slope is in x, y defined in terms of x, y coordinates. And so here are some calculations. So once we know the formula, you just have to calculate the derivative of y and derivative of the x. Do the conversion first. So convert into these are pictures. This is the conversion, my standard parameterizations. Okay, and I take the derivative with respect to theta, and take the ratio of dy d theta dx d theta, and plug in pi over 2, then you get a slope. Okay. So, well, let you check the arithmetics in here. Okay, and here's another example. The question asks where the slope is 0. What slope is 0 is when the denominator of dy dx is 0. That's dy d theta. Okay. So therefore, all I check when's dy d theta 0, and I take the derivative with respect to theta. And set it to 0, then I get a trig equations. And as in general trig equation, you would like to convert that into one single function, sine or cosine. And this problem, the algebra works out because the sine square can easily convert it into cosine. And then you wind up with the equation cosine, then you factor, you extract the answers. Okay. And one of the problem you might want to think about it is where do you get this? Where do you get the where the tangents vertical? Okay, where's the dy dx undefined, if you like, UDF. Of course, I mean then the calculation you'll be checking is when is this equal to 0 for this problem. So it behooves to work through these problems similar to what algebra you have here for finding where the vertical tangent lines are. It's easy on the graph, okay, to tell us where it's on the graph. Okay, convert from polar coordinates into the parametric form for the arc length. Okay, for the arc length interval, the parametric form is y prime t square, or x prime t square plus y prime of t square root. Then integrate these. Okay, then t is the parameters, right? Here's a theta. Okay, it just focuses on polar coordinates, so the parameter is the angle, so everything converted to theta, then we'll get this nice clean formula. Okay. You can work it through. You will find out it's very easy to convert that. This actually becomes that easy algebra. Then again, a lot of these formula for calculating area, arc length, etc., require you to square. Notice the square, okay, in the formula, which means if you have problems involving sines and cosines, you want to integrating things of sine square, cosine square, okay. And so that's one, if you to remember how to do that algebraically, we're going to use converting square formula into double angle formula. Okay, well, going too fast over here. Okay, here's a problem that works out perfectly. So you're integrating integers, and then in this problem, what's pointed out, you need to watch out is as theta go to 0 to 2 pi, what would happen is this actually will wrap around the circle twice. Hence, you get 4 pi. Okay, 2 loops overlapping each other. Okay. Here's another example from the arc length of this, and I'm going to let you read the algebra. Okay, so how it works. So okay, so the integration part, I'm not going to repeat. Okay, so these are the basic problems in terms of arc length formulas, and just as in the case in the parametric forms or in the regular y to f of x form, it involves a square root, and so the integral. The integral usually involves some tricks, and or else you have to create a problem that's with strange power or kind of strange form to make the integration come out nice and clean. Okay, so just a formula for arc length. Okay. Now let's come to area. How do we calculate area? Okay, what we mean by area is that in between 2 angles. So when theta is at angle A and angle, it goes between angle A and angle B, and within the curve I equal to f of theta. I can imagine this as sort of a radar screen, and I have these sweepers that sweeps in and bounce out the boundary of the curve, and then you find out where it is as it swipes through. Okay, and we want to calculate the area. Okay, and we're going to again use fundamental theorem of calculus, and I'll basically treat it as a function. R equal to f of theta, and the theta go from A to B. So I'm going to cut A and B. No, think of this as theta from the number A to B, and I'm going to cut into very little partitions, and each one's delta theta. Okay. So, and then I'm going to find out what a function value at each one of these partitions. Okay. Now, this is the XY pictures. Where does the functions reflect when we on this theta from A to B, when we make different value of thetas? Well, at theta 1 over here, of course, it means goes out, and that way it's theta 1, and theta 2 over here, and of course it means the angle now theta 2, and it goes out there. In other words, each one of these partitions, it cuts the fan shapes into slivers. For every delta theta you increase, you slice off a sliver of area. Okay, now how big is that one area? Well, we pretend it's sort of like a circle. So S1 is roughly like a very thin slice of pizza with the round edge. Why do I use a round edge for the calculation? Because it's a circle. I know how to calculate a sliver of a pie. But if you okay. So we're going to pretend that little sliver, and it's approximately a circle. And then the formula for that particular area, S1, it's calculated. Okay, this is the area of the circular slice. It's roughly S1. Okay, and of course, S2 is roughly the second slice. Okay, and each slice changes because the radius changes, depending on that. Now I add them up. Okay, let n goes to infinity, then the fundamental theorem of calculus with purely algebraic, so this sign turns into an integral and spanning from A to B, and this turns into the differential d theta, and this of course turns to the function r and r. 1/2 comes out. So, and this is the area for the area between the two angles. Okay. Again, we are integrating r to r squared. So if the formula r involves sines and cosine, then it would be integrating sine square or cosine square. And here are some examples how the formulas, using this formula, example over here, compute the area of a circle. Okay, of course, it come out with pi r squared or pi k squared in this case. Again, watch out the number is swiped through. Okay, if I put these circles, if I put as a sine of theta, then you wind up with 4 pi. Okay, pi, 4 pi k squared. Okay. Yeah, like here. If I do it and integrate that, okay. I integrate from 0 to pi because why? Because from 0 to pi, the area is swiped through once. If I do 2 pi, I will get twice of the area. And here's another example for the cardioids. And over here, the question asks you to find the area enclosed. Okay. So we calculate that area. Okay. So that's what yeah, I'll let you read the calculation. Right. It asks for the between 0 and 2 pi. This is little chunks over here. So this is the, again, I mean, you convert this into double angle formulas to do the integrations. Okay. It's a reminder for that little algebra. Okay. And then the next is the formula for area trapped in between two borders. Okay, the big radius and inner radius, little r, and outer radius, big R. And then of course you'll be taking away from the big areas, take away the area in here. So that's why you have the subtractions. Okay, and then here is a problem. Calculate that. So another problems that in this type of questions, you need to find the boundaries of the A and the B. Where are the angles that this talks about? In between what and what? So that involves solving for intersections of polar curves. And that's a trigonometric questions, trig equations questions. Okay, sometimes it gets a little tricky. The safe way to do it is always graph it out, see what you can. Usually the problem will be fairly easy and symmetric. So you can usually read out what the angle is supposed to be. Okay, and do both, solve the questions and graph and confirm that the angles that is between A and B's when you do the set up the integrations. Okay, so here we solve for the two angles. So angles between theta is between pi over 12 and 5 pi over 12. So I integrate limit from 5 over 12 to 5 pi over 12, and the outer squared minus 2 squared. Okay, inner square and half of that, and double it. Oh, no, going to quadruple this. Okay, so that's one of the area. Okay, we only count one piece, and there are 4 pieces. That's why we multiply by. Okay, so these are the basic algebra type of problems for area, arc length, and the derivative problems using in polar coordinates. Okay, bye bye. Until next time. Bye bye.